Today, in this session, I'll be talking about energy and exergy analysis of chemical looping combustion, integrated organic Rankine cycle biomass-fired power plant. So this is the outline of my talk, right? So I think this somewhat in continuation with what I presented in last lecture. So hence, I would like to skip the introduction part, right? So because there, I have already given some picture on uh, use of renewables, right, and fossil energy in power generation and the corresponding consequences, right, and what are the methodologies to curb the CO2 emission, right, precautions or policies we have to adapt, right. So in this session, first briefly I'll talk about the scope of renewables, right? Then briefly about chemical looping combustion, because the introduction of this chemical looping combustion concept, right, is already presented by my colleague Dr. P.V. Suresh in his presentation. Uh, so that I'll cover maybe one or two slides, then followed by CLC, chemical looping combustion of biomass. There I'll be discussing these steps in a bit detail, methodology, flow sheet simulation, right, and tuning of some important parameters so that we can improve the performance of that process. The next, energy, exergy, and economic analysis of the proposed configuration, right, and comparison with the conventional. And at the end, based on the time availability, right, so I would like to show some simulations on Aspen, right. So what I'm planning to do, since this FDP more towards the use of CO2 as a working fluid, right? So whenever we are using this CO2, right, the primary or most important point is we should estimate the properties of CO2 at different operating conditions with the most now at the more accuracy, right? So let us see how to estimate the properties of CO2, right? Maybe pure component properties, right? Primary and secondary, and some properties at high pressure and high pressure conditions, supercritical state, right? Then I also would like to show the simulation on uh, the CLC biomass, right? So how we simulated that process, right, in Aspen, right? So just I would like to present the advantages and disadvantages of disadvantages of renewables use in renewables usage in power sector, right? So because we have been talking about now fossil fuels have to be replaced with some green energy sources, and the most promising green energy sources are this, right? If you look at the advantages and disadvantages, for example, bioenergy, right? The main advantage is we have enough feedstock, right? Or we can continuously regenerate this feedstock, and it also ensures the national energy security policy, right? And it enhances the rural employment, right, and agriculture economy if the biomass we are getting from the agriculture products, right? And the low CO2 emissions, or at least they are CO2 neutral compounds, right? So the main disadvantage because of the using bioenergy extensively in power sector, right? So it affects the natural vegetation, right? So if we wanted to form the commercial crab, right? So which is more suitable for energy generation, right? So that may affect the natural vegetation, right? And deforestation may also happen. So like that, if you look at solar energy, it is available in abundant quantity, right? And it also have very low carbon footprints, right? But the main disadvantage with the solar energy, it is fluctuating in nature, right? So uh, you cannot harvest the solar energy 24 hours in a day, right? And relatively at present it is a high cost technology, right? So like that, if you look at the wind, it has its own advantages and disadvantages, right? Pollution free and easy accessibility, right? And feasibility of installation in rural areas, right? But again, disadvantages is it is unreliable source. Noise pollution will be there. High cost technology at present, right? So hydro energy, so highest plant life, right? In India, most of the green energy source is this, right? So the after fossil fuels, right, we produce more power from this water, right? So or from the water tanks, right, dams, etc. So high storage capacity, operation flexibility, right? So this also requires significant area, right, which affects the wildlife population, biodiversity, right? And since we are storing this water, right, it also degrades the water quality, right? And nuclear, yes, as I said, this is the only fuel which have high capacity factor, right? The capacity per unit weight of the power capacity per unit weight is much high compared with any other fuel, right? So CO2 emissions will be less, but hazardous emissions and other hazardous waste generation will be high, and we have to treat this properly, right? So like this, we have advantages and disadvantages using this different types of renewables, and in order to make this technologies economical, right? So we have to effectively capture the advantages, and we try to minimize the impact of these disadvantage parameters, right? For example, if you consider solar energy, it is since it is fluctuating in nature, right? So you can capture maximum solar energy in daytime, right? And you can store it, and that can be used in the absence of light or during night, right? But that requires battery technology, right? Or high capacity power storage devices, right? So different options are available there, right? So you can use directly batteries, right? Or some high density fuel synthesis also you can do at daytime, and in the nights that fuel can be used for combustion, and you can generate the power, right? For example, synthesis of hydrogen using solar, right? So you can use that hydrogen maybe in power generation process, right? Whenever be required, right? Or in the absence of solar. So like that, you can minimize or you can find the alternates for the disadvantages available with these green energy sources, right? So if you do that, we can make this power production from these green energy sources, right, as a sustainable option. Okay. Yeah, this is just a repeating slide, right? I hope my colleague already presented, right? So we have different capture technologies. Yeah, again in this talk, I'll be talking about more on bioenergy, right? Our power production from biomass, where uh, we are interested to capture whatever the CO2 released from that power process, right? And so that we can make that technology as a carbon negative technology, right? So as you already know, we have different options, right? Post combustion process, pre combustion process, and oxy combustion process, and each has its own advantages and disadvantages, right? But the combination of these two, post and pre oxy combustion process, right? So we know the in the literature, a new process is derived that we call it as chemical looping combustion process, right? So where we use two reactors, right? Instead of single combustion reactor, we use two reactors, air and a fuel reactor. You can see these reactors here, right? And we also have cyclones to remove the solid suspended particles from the gas, flue gas or air, right, coming out from this process, right? And in air reactor, right, what happens? The reduced form of metal oxide will be oxidized, right? And that metal oxide, and again, go to fuel reactor where combustion happens, right? And basically, it supplies the oxygen in fuel reactor, right? So you can see, right? So in this fashion, the metal oxide, right, will be continuously runs in a loop, right? So Fe2O3, this is the actual form of metal oxide, right? So will be, reacts with biomass or whatever the fuel we are considering in this fuel reactor, and basically this supplies oxygen for combustion process, right? So the fuel in the presence of oxygen, right, combustion happens, and you will get only CO2 and H2O, because we are supplying only oxygen, right, by means of reducing the metal oxide, right? So the reduced form of metal oxide will be sent to air reactor, right, where it reacts with air or oxygen present in the air, right, and again will be oxidized to Fe2O3, right? So the form of metal oxide and other things can be, depending upon the type of atmosphere provided in the fuel reactor, right, and the conditions, right? So for example, we have Fe2O3 here, that can be reduced to FeO or Fe or Fe3O4, right? So that the reduction is, depends on many parameters, and ultimately, we would like to reduce this material to Fe, so that you can see, if it reduced to Fe, it releases more amount of oxygen, so that the combustion can happen easily, right? And if it continuously, the entire Fe2O3 reduces to Fe, right? So the amount of metal oxide required will also be minimum, right? So there are a lot of advantages, but that may not happen, right? That depends upon different parameters, and most often what we see, so the reduced forms, right, the reduced form of metal oxide contains all these compounds, some amount of Fe, some amount of FeO, some amount of Fe3O4, right? So that reduced form we sent to a reactor, where again it oxidized into Fe2O3, right? So basically, this is a equilibrium reaction, right? We uh, control the forward and backward reactions based on the temperatures provided this, right? So basically, this fuel reactor, whatever happens, it's endothermic process, and air reactor, the oxidation of metal oxide is net exothermic process, right? So in this way, we avoid the direct contact of air with fuel, right? But or oxygen, air with fuel, and from air, we are only transferring oxygen to here by means of metal oxide, right? So now if you look at this process, right? So after combustion, right, we don't have any further requirements for separation, right? So air is the lean air, right? So less concentrated, less oxygen concentrated air is leaving from the air reactor, and in a flue gases it has only CO2 and H2O if there is any steam, right? So that CO2, or the from this mixture, H2O can be easily separated by condensing, and CO2 can be used for any other purpose, right? So the main advantage here is, while combusting itself, we are ensuring there is no contact between air and fuel, right? So, and it's like almost oxy combustion, right? So that we are getting pure CO2, right? So the concept is derived from this principle, right? So any reaction, right, in general can be decomposed into multiple sub-reactions, right? Using a different chemical intermediates, right? So that those are reacted and regenerated, right? So if you look at the intermediates, right? So mainly the intermediates are formed from Fe2O3, right? So Fe2O3 converted to Fe and again regenerated to Fe2O3, right? In this process, we you know modified the conventional combustion process into as per our requirements, right? Our emphasis mainly on let us not use direct air for combustion, right? But we want oxygen from air. So that process we attain by using this principle, right? So that kind of reactions in nature we call it as chemical looping, right? Then why we concentrated on chemical looping combustion of biomass, right? So so this is the main aim, right? By 2050, right, the CO2 emissions from the power plant should be reduced to 20% of the 2009 emissions, right? So you can see the statistics, right? So we have a lot of greenhouse gas emissions in 2009, right? So at least now we should limit our emissions in 2050 to 20% of that value, right? So ultimately, the options are we should minimize the use of coal, right? So when we minimize the use of coal, right, we have to explore the green source options, right, where we have like solar, biomass, wind, and other things, right? And when we use fuel, but we cannot completely eliminate the usage of coal, right? So we have to, even if we use coal and biomass, right? So from these power sources, right, we have to capture CO2, right? So that's why we interested to integrate even this CO2 capture technology for biomass so that it can become a very attractive option, right? So whatever the damage is doing by this fossil fuels, right, so can be compensated if we apply this technology because it is a CO2 negative, right? So, and not only that, we have a lot of biomass reserves. Basically, all agricultural countries, right? So we'll be having a lot of biomass, right? So if we harvest that properly, right? So we'll be having a lot of energy source, right, in the form of biomass. And usually biomass based plants are in general small capacity based plants, right? So they can be installed as a grid independent power generation sources, right? And by using this we can eliminate the rural energy demand problems, right? So because this is also one of the most concerning problem, right, to supply the power to certain rural areas where some areas are geographically very difficult for approach, right? So there you can set up this small capacity grid independent power plant so that you can meet the power demand problems there, right? So as I said, this is carbon negative, right? So that now we can make this as a very sustainable option to curb the CO2 emissions, right? So, and we can, yeah, this is what we have to use ORC cycle, right? Because it's a small capacity plant, so uh, uh, steam cycle may not be efficient, right, to handle these small capacity plants, right? So this is a typical ORC cycle we have, right? So evaporator, turbine, condenser, pump, right? So this is the heat transfer loop from where we get energy, right? Using this thermal fluid, and that will be transferred to organic fluid. So though we are saying for small capacity we have to use ORC, right? So though the efficiency of ORC plant is slightly lower than the steam cycle, right? But it has its own advantages, right? Uh, the advantages are highlighted here, right? It mainly eliminates the superheating, which avoids the use of expensive materials, right? Because this operates at very low temperature, means relatively low temperature region, right? And we since we use organic fluid, the condensation temperature will be less, right? So there's a less chance of condensation in turbines, right? And it also have the vapor and liquid density of this fluid is more or less same, right? It doesn't require recirculation in boilers, right? Due to the low density differences between vapor and liquid. So the first ORC, biomass field ORC power plant, right, is installed in Switzerland in the year of 1998. After that, the research is continuously going on in this area, right? And we have different studies where the main objectives are improve efficiency by cycle modification, or what is the best working fluid, right? And optimization of operating conditions so that we can improve the performance, right? So our work is also in tune with the objectives, the main objectives serving in the literature. So here our objectives are to develop a novel energy efficient CLC integrated BFE configuration for power production from sugarcane bagasse biomass, right? So this is a biomass we have considered, and we did some thermodynamic analysis, right, to optimize the key operating conditions and improve the energy and exergy of efficiency of the process, right? And the performance also compared with the conventional biomass, and uh, you know uh, concluded the merits of each configuration. So the methodology adopted here is first we validated the steady state simulation of conventional biomass combustion power plant, right, which is integrated with the ORC cycle, right? Then we simulated the uh, novel biomass CLC power plant integrated with ORC, right? And we did this energy exergy analysis, right, and economical analysis, and compared the merits and demerits of each process, right? And also, after exergy destruction, after exergy analysis, we also identified the bottlenecks of the process where the improvement is possible, right? So the validation first, uh, the coal-fired power plant and ORC cycle are simulated, right, as independent units, independent processes, right? Uh, then they are integrated, right? So before integration, whatever the coal feed in the combustor used is replaced with biomass, right? And the performance is recalculated. Then integration of this biomass fired power plant with ORC cycle is done, right? And here the auxiliary power consumptions in the plant are considered to be 5%, right, as of the gross power output. So this is the scheme of conventional biomass fired power plant. So this is a combustor, right, where biomass is burned by using air, right, compressed air. So then flue gases, right, we transferred to heat exchange unit, where the energy from these flue gases are exchanged by using this uh, thermal fluid, right? So the thermal fluid in general, generally kept in a tank, right? So from the tank, this will be circulated, right? and ultimately this tank will be having a steady state temperature, right? So, and the high energy thermal fluid, right, will be sent to evaporator, right, where the energy will be transferred from thermal fluid to this organic fluid, runs in a ORC cycle, right? So again, this organic cycle, ORC cycle, already we have discussed in the last presentation, right? So where we have turbine, condenser, and pump evaporator, right? So this is a schematic view of conventional CLC integrated, sorry, conventional biomass, right? So here, this is a flow sheet of ORC unit, right? So where we have, see, this is the flue gas, and this is the heat exchange unit, where the energy from flue gas is transferred to thermal oil, which is running in this loop, right? So this evaporated transferred the energy from thermal oil to ORC fluid. This is the ORC cycle. Okay. So now that the results of that conventional biomass fired power plants, right, are generated and kept for comparison with the uh, biomass CLC power plant, right? So here, uh, first, to simulate biomass CLC power plant, what we did, we developed a steady state flow sheet for CLC integrated biomass power plant at Indian climatic conditions, right? So in that, uh, the development is the simulation is started by, first conventional power plant is simulated, right? Uh, uh, and from that conventional power plant, right, so the boiler of conventional power plant is replaced using this air and fuel reactor setup, right? So where the combustion now happens by in the form of or in this configuration, right? Then so biomass is fed to the fuel reactor, where the metal oxide supplied oxygen and combustion happens, right? And the reduced form of metal oxide again sent to air reactor, where it oxidized and sent to fuel reactor. This is having a loop, right? And here the metal oxide used is Fe2O3, basically, which supplies oxygen, but that is supported on 30% Al2O3, because uh, high temperature operation, right, may center the Fe2O3 metal oxide during this oxidation reduction process, which reduces the effectiveness of that metal oxide, right? So to avoid that, what we used, we have used some inert material Al2O3 and formed and synthesized a composite, right, which is having 30% Al2O3 and 70% Fe2O3. So this is the CLC integrated biomass fired power plant, right? So typically this is the combustion section, right? So you can see from here, to the combustion section, we are adding biomass, right? We are also adding air, right? But if you look at the exit streams, right, so we have hot depleted air, means less O2 air is coming out, and hot flue gases, which are having only CO2, right? So how this is happening, you can see from here, Fe2O3 is running in this loop from fuel reactor. Again, we have cyclone separator, so that cyclone separator separates Fe2O3, and that is again going in this way. So this is the actual loop of Fa2O3, right? And from in a reactor, we are sending air. So that reduced form of Fa3O4 reacts with air and it forms Fa2O3. And the lean flue gases are coming out from this air reactor like this. And in fuel reactor, combustion happens, and here the gas and solid mixture separated, and the concentrated CO2 is coming out, right? And this process is also, this chemical looping combustion process, right? We are carrying out at very high pressure. It's about 10 bar pressure we are maintaining in this unit, right? So the air also, is required to send at that pressure, right? So the same hard depleted air will also come at very high pressure. So that's why we are using gas turbine, right, to generate power by using this hard depleted flue gas, sorry, hard depleted air, right? So this gas turbine generates power from this by extracting energy from this hard depleted air, and the exhaust exit air again will be sent to this evaporator, right, or heat exchanger unit, right, where the remaining energy, right, will be extracted, and the cold depleted air will be released into atmosphere. Okay. And the concentrated CO2, right, which is at 11 bar, right, uh, this is operating at 11 bar. So this we are directly, after the thermal energy extraction, right, at constant pressure, right, we are sending into uh, flash where we separate water, and the final CO2 we are compressing to CO2 ready sequestration pressure, maybe 100 bar, something like this, right? So that it can be directly stored, right? And some amount of CO2 we are sending back to this fuel reactor so that it can be utilized as a fluidizing agent, right? So here we can use CO2, which is available here, or sometimes even steam also we can use as fluidizing agent, right? But the same CO2 comes out from this line, from this loop, right? So this is about the operational scenario of CLC integrated power plant, right? So now the thermal energy from CO2 concentrated stream and hot depleted air, right, is transferred to this thermal oil, right? So the thermal oil again transfer energy to this organic fluid, and that organic cycle also, gives some power, right? So now we have power generation from these two cycles, right? One is ORC and one is CLC itself, but here we are using gas turbine to generate the power. Okay, so you can also see the different lines, right, using different color lines and dash lines, right, so that you can easily analyze what the each line represents. So this is the flow sheet of CLC unit, right, in CLC integrated power plant. Here we have a reactor, and here we have fuel reactor mainly. Right. So from the air reactor, whatever the lean hard depleted air is coming out, that is sent to gas turbine where power production happen, and this will go towards that heat exchanger unit for extraction, right? And whatever the CO2 is coming, that will also directly go to heat exchanger unit for giving the, or for removing, giving the thermal energy to hot thermal fluid, right? So for that configuration, we did energy and exergy analysis, right? So the what is the advantage of energy and exergy analysis, right? So energy analysis basically works on first law of thermodynamics and gives us what is the quantity of energy, right, and its amounts and exchange, etc. This is more or less similar, like, if for a patient, right, if is feeling a chest problem, right, maybe breathing problem or some problem with lungs, etc., right, so we can observe the functioning of lungs by observing the sound, right, by using the stethoscope, etc., from outside, right. So the exergy analysis is more or less similar to observe the same disease by using the X-ray, where now we can have a clear picture, right, what happened and etc. Okay, so it's a quality of energy, right, utilized, right, and the quality of energy is being wasted, right. Those information, right, will get from the exergy analysis, right. So these are the formulas used, right. So to calculate work output, right, and efficiency, right, gross and net efficiency, right, and and exergetic efficiency also we calculated by using this formula, right. So this is energy efficiency and exergy efficiency, and exergy destruction efficiency, right. You can calculate exergy destruction by using this formula: exergy in, total amount of exergy in minus total exergy out. You can call it as exergy destruction, right. And exergy efficiency, you can individual unit exergy efficiency you can calculate by using this formula, right? And ecological assessment also you can do, right, by finding out the specific CO2 emission, right, and carbon capture efficiency, right. Specific CO2 emission, uh, amount of CO2 released per unit amount of network generated, right. So capture efficiency, amount of CO2 captured from total amount of CO2 generated, right. So using these formulas, you can calculate the energy exergy efficiencies. So as I said, after simulating the steady state CLC integrated biomass power plant, right, we did some analysis on few critical variables which can affect the performance of this energy exergy performance of the CLC integrated biomass, right, in a significant way. Uh, First parameter is effect of oxygen carrier to biomass ratio, right? How much amount of oxygen carrier and the ratio between how much amount of oxygen carrier is used per unit amount of biomass, right? So, for example, as we are increasing the oxygen carrier amount, right, per unit amount of biomass ratio, right. So initially, what we observed the net power output, right, is increasing. So the reason for this is, and not only net power output, you can see gross power output and power output from combustor and power output from overseas turbine, right? So this gross and net mainly, calculated from these two parameters or these two profiles. So you can observe the net gas turbine output power is increased and ORC turbine power output is also increased as we increase OC to biomass ratio, right. So the reason for this increase is mainly, like, as we increase the OC, oxygen carrier, right. So the amount of oxygen required for complete combustion, right, is meeting, right? Because this oxygen carrier supplies the oxygen in fuel reactor, right? So the amount required to completely combust the biomass, right, is available, right? Uh, as as the biomass combustion is increased, right? So it releases more amount of energy, right? And that more the increased amount of energy is ultimately leading to increase the power outputs, right? So you can also see the other variable effect as we increase the OC action carrier, the amount of air required also increased. Why? Because more amount of metal oxide is used, right, and the more oxygen is supplied, right, or the more amount of oxygen carrier is reduced, and the reduced oxygen carrier is coming ultimately comes into air reactor, where we need more air, right, to re-oxidize that reduced form of metal oxide. So that's why the air amount is also increased, right? And the last profile, this power consumption, right? So this power consumption mainly associated with the uh, compressor required to to compress the power associated with the compressor, right, which is used to compress the CO2, right, to sequestration ready pressure. Let me check. Yeah. So this power required to compress the CO2 to sequestration ready pressure, right? And all other power requirements, right? Anyway, that 5% is auxiliary power. And if you look at this compressor net turbine power output, right? This is net turbine power output because this includes the power required for even air compressor as well. Okay. And the net ORC power output, I think this include the power required for feed pump as well. Okay. So in this cycle, whatever the power requirements after meeting the power requirements, we are calling it as net. So now this is the only profile left, right, which needs to be discussed now. So this represents power consumption. Mainly, this is associated with the compressor power, CO2 compressor power, right? So why the power requirement is decreasing, though the CO2 emission rate is also increasing, right? When there is a more combustion, right, more amount of CO2 released, right? So surprisingly, right, when we are using the oxygen carrier requirement less than oxygen carrier amount less than the theoretical requirement, right, obviously there will be more CO formation because of incomplete combustion, right? So the amount of power required to compress the CO is more compared to amount of power required to compress the CO2, right? So that is the reason, right? As we are increasing the OC, right, slowly complete combustion is happening, right, and CO formation is less, CO2 formation is more. As we are getting more amount of CO2, right, the power requirement is decreased, and after some time, right, the power requirement is constant because the amount of CO2 coming is constant. After complete combustion, that is the maximum value of CO2 we get, right? After that, we will not be having any more CO2, any increase in CO2 amount in this stream, in this stream, right? So, and after this is the maximum, power, right, we are getting, right, and where maybe complete combustion is happening. So after this, if we increase further the oxygen carrier, right, so the oxygen carrier amount will increase, but that amount will act as only inert, right? And it continuously runs in this loop, right? So it unnecessarily carries certain amount of heat, right? Heat in this loop without giving that to flue gases or etc. And as you are increasing OC amount, the operating temperature, right, also decreases, right? So that decrease in operating temperature also reason for decreasing the overall efficiency, because beyond this point there is no complete combustion is happened, right? There is no other heat source, right? So if you are adding any extra mass in this loop, right, that unnecessarily decreases the operating temperature and carries heat, right, in the form of inert medium, right? So these are the reasons for you know decreasing the power outputs after certain time. So based on this analysis, we have found out a optimal OC to biomass ratio value, and that we kept constant for further study, right? And efficiencies also you can see, right, more or less in the same region we got the maximum efficiency, and that optimal value we have considered, right, as a OC to biomass ratio. For a given OC to biomass ratio, right, in the CLC integrated biomass power plant, right. Next, we changed air to air and fuel reactor operating pressures, right. So these reactor operating pressures, right. So as we increase operating pressures, right, so the net gas turbine power output is increased, right? And though ORC power output is decreased, but you can see the net power output. This is what the final parameter we are interested in is increasing for some time, along with the gas turbine output, and after some time it shows a decreasing trend, right? So how we can increase the operating pressure in air and fuel reactor? So by using this air compressor, right? So initially, as you increase the air pressure, right? So it carries means this streams, right? Carries energy at high pressure, right? That is leading more amount of power extraction by using this gas turbine, right? So the power extraction will be more as we are increase as we are operating turbine at high pressure, right? So that is leading to more amount of power extraction from this gas turbine, and that is the reason for increasing trend in this, right? So see, after complete combustion, the amount of energy released will be constant, right? So but only thing is from that available quality of energy, how much effectively we are extracting, right? So as the gas turbine is able to give more power as pressure increases, right, it utilizes more energy from the stream, and the leftover energy which is transferred to this thermal oil cycle will be less, right, which is ultimately uh, reducing slowly, right, the ORC cycle, ORC power output. But overall, the net power output is a summation of net gas turbine output and ORC power output. But the rate of increase of gas turbine power output is very high. That's why we are seeing the increasing trend in net power output. And after a certain time, so the net power output is decreased. That is mainly because as you are increasing compressor power requirement, air compressor power requirement, right? So there is a breakthrough, right, where the rate of increase in gas turbine power output, right, is less than the rate of increase in compressor energy requirement, right? So because of this net difference, right, so slowly the gas turbine power output is slowly following the decreasing trend, because here the air compressor power output, rate of increase in air compressor power output is dominating than rate of increase in gas turbine. Sorry, rate of increase in air compressor power requirement is more than rate of increase in gas turbine power output, right? So this is a reason, right? After certain time, after certain point, right, so we are observing the net power output decrease, right? So this point we have, considered as the maximum uh, pressure, right? So which is yeah, which is around in between 10 and 11, because you can see this. So this is where the maximum is, right? Slowly after that, we are observing decreasing trend. So that's why we have selected this as a uh, feasible operating pressure, right? So the same thing you can also see from here, right? So the efficiencies and other things, right? So where we have gross energy efficiency and the net energy efficiency, right? So this is the net energy efficiency profile, where we have maximum in this range, 10, 11, 12, something like that, right? So by considering that operating pressure, right, now we have analyzed the third important parameter, which is air reactor operating temperature, right? So this is the air reactor operating temperature we modify as we are changing air reactor operating temperature, right? So the gas turbine power output is increased to some value, and after that it is decreased, right? So the reason for this increase in gas turbine power output, uh, as we are increasing air reactor operating temperature, this also represents the fuel oxide uh, 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 temperature, right? So more amount of heat transferred to fuel oxide, right? Where the hot flue gases temperature also increases, right? And because of high temperature, right, as temperature is increased, there will be a noticed increase in net power, but after some time, we notice the decrease in power requirement, power output. That is mainly because as we are increasing air reactor operating temperature, the the air amount of air circulated is decreases, or flow rate of air sent is decreases. This is mainly because in order to operate this air reactor at a certain temperature, right? So we have the only controllability with reference to amount of air we are sending in, right? Usually we send air excess to the theoretical requirement in order to completely oxidize that metal oxide, right? So now what we are doing, so we are slowly reducing that air flow, right? And towards, we are bringing that airflow towards the theoretical requirement, right? So as the amount of air flow in decreases, right, so the same amount comes into gas turbine into gas turbine for power production, right? As the amount is decreasing, so after after certain time, right, so the gas turbine power output is decreased. The main reason for this is, so the gas turbine or this setup, you have to see this as a turbine and the associated air compressor, right? As amount of air in is decreased, the power required for air compressor is decreases, right? So in this profile, you can see the rate of increase in gas turbine power, right? Power production is more, uh, and sorry, what I can say here, the rate of decrease in air compressor, the rate of decrease, the rate of power requirement, the rate of decrease in power requirement of the air compressor, right, is very high, compared with the rate of decrease in gas turbine power production, right? Because as the amount of air decreased in gas turbine, right, amount of air entering into gas turbine decreases, the power production from gas turbine also decreases, right? So one is power production, this is power consumption, right? So the power consumption of air compressor also decreases because we are sending low air, less amount of air. So the rate of decrease in power consumption, right, rate of decrease in power consumption, right, in air compressor is much high than the rate of decrease in power production in gas turbine, right? So because of this kind of profile, right? So the net power we are always calculating by using the power production from gas turbine minus power consumption by air compressor, right? So since the power consumption of this air compressor is decreasing with very high rate, right? So as as operating reactor air temperature changes, as the air flow rate is decreases, so the net turbine output we are seeing is increasing. And there is one point where the maximum is seen, right? After this point, rate of decrease in power production is greater than rate of decrease in power consumption of air compressor. So this profile follows this trend, and this profile follows rate of decrease in power consumption much greater than rate of decrease in power production. Right. So this is a reason for now observing the net gas turbine output reaching to maximum value and again decreasing. Right. Whereas the ORC turbine power output is continuously increasing because as we are increasing the temperature, right? So the flue gases are coming at very high temperature, and this may be also coming at relatively high temperature. So more amount of energy being transferred to this thermal oil followed by ORC fluid. So that's why the uh, ORC power output is continuously increasing, right? So if you look at the net power output, so because of the high rate of increase in turbine power output, right, and as well as ORC power output increase, you are seeing net power output increasing some value, right? And after this, though there is an increase in ORC power output, but rate of decreasing in net turbine power output is more. That's why the net power output, overall net power output shown is decreasing trend, right? So that's why, based on these profiles, we have identified some optimal operation temperature, which is near to 1050 or something, right? And these are the final important parameters, and you can also see how the ORC performance is now increased as we are changing the parameters, right? So as it is energy efficiency 18.73, and at optimal air and fuel operating temperature, it is changed to 18.76, and air and reactor operating temperature, the efficiency is increased to 18.94. and similarly the corresponding exergy efficiencies, right? And we have also did the study on different ORC fluids, going to be can be used in ORC cycle, right? And we found that R600A, right, has maximum net power output, followed by R245 and R123 and tolling. These are, I think, different types of fluids: high temperature organic fluid, right, medium temperature organic fluid, and low temperature organic fluid, etc. Right? But though this found to be more effective, right? But by considering all other parameters like toxicity and other parameters, right, mainly hazardousness, etc., we selected R245 FA as the most suitable fluid for running in ORC cycle, right? And the ORC cycle is again, the performance of ORC cycle is improvised by uh, extracting waste heat energy, by using the recuperators, right? And ultimately, after waste heat extraction, right, the total CLC power plant, efficiency is increased to 20.8 from 18 point something, right? So this configuration, you can see, this is the CLC integrated biomass fired power plant, right, equipped with recuperators, right? So the waste heat from CO2 stream, right, is extracted, and also the waste heat from the stream which is coming out from the turbine, right? Usually we remove by using condenser, right? But it is first extracted by using one recuperator, and again the remaining heat is removed by using condenser, right? And whatever the waste heat plan to extract, right, that is directly transferred to the ORC fluid, right? So for that, what we did, the ORC fluid coming out at high pressure from pump is divided into two streams, and one is used to extract waste heat from CO2 stream, and one is used to extract waste heat from the ORC fluid coming out from turbine. Right? So this fluid again directly sent to evaporator, right? And the stream which is used to uh, used to extract energy from CO2. I think it is reaching direct operating temperature, right, which required that the inlet of ORC turbine, right. So hence these two are again mixed here and directly sent to ORC turbine. Right. So this configuration resulted significant increase in overall efficiency, right, from 18.7 to 20.8, etc. So now this is the uh, comparison of different parameters, right? Uh, for conventional biomass power plant and CLC biomass power plant, right? So net power consumption is high in CLC because we are using CO2 compressor, right? And we don't have any gas turbine in conventional, so that's why there is no power output from gas turbine, whereas we have significant power production from gas turbine, right? So since we are using only ORC fluid, right, the power from ORC turbine will be high in conventional, slightly less in CLC integrated, right? So you can also see the net power production, right? So which is very high in CLC integrated biomass power plant compared to conventional for the same amount of energy supply, right? So these are the same discussion related to that graph, right? And we have also compared the efficiencies, right? So gross energy, net energy efficiency is about 11 to 12% in conventional, whereas it is about 18 point or close to 19% in uh, CL's integrated biomass power plant. Right. So net exergy also you can see from the graphs, right? So the CL's integrated biomass power plant has significant high exergy compared with high exergy efficiency compared with conventional. Right. So we also did this ecological assessment, right? So here just we saw different CO2 analysis parameters, right? How much amount of CO2 emitted, right? So grams per second, and how much amount of CO2 captured, right? And efficiency, right? Specific CO2 emission means per kilowatt of power produced, how many grams of CO2 emitted, and you can see the conventional biomass fired power plant is emitting significant amount of CO2 to atmosphere, and these are the annual CO2 emissions, right? And emission rate per unit of fuel calorie value or fuel power, right? And annual CO2 emission avoided per unit of fuel, right? So we have a sustainable and attractive option, right, with CL's integrated power plant in terms of CO2 parameters as compared to conventional BFPP. And these are exergy analysis of individual units for CL's integrated plant and conventional plant, right? So here the combustor means what we did in conventional, right? This is simply combustor. In CLC, this is combination of a reactor and fuel reactor, right? And you can see, individual units have different exergy and exergy efficiencies, right? So ORC turbine has high exergy efficiency, but whereas combustor, we need some attention on compressor, air compressor, right? Thermal oil tank in case of CLs integrated, mainly evaporator, right? So this evaporator, if you increase the efficiency of this evaporator, right? So the overall power output can be increased marginally, right? So these are the unit-wise exergy distraction profiles, right? So here also, yeah, fuel reactor we have high exergy distraction, right, and followed by air reactor, right? So you can check air compressor, right? So you can concentrate on these units where we have maximum exergy distraction, right? So these units, can be improved in performance so that you will get the better efficiencies. And these are the conclusions, right? So we first found optimal conditions for operating important operating conditions for CL's integrated biomass fired power plant, right? As we fine tune, the efficiency is also increased to high value, right? And about 20.8% increase in ORC turbine output is observed, right? As we extracted heat using recuperator, right? And so the energy and the exergy efficiencies of biomass CL's integrated biomass power plants are found to be 21.5 and 18.56, whereas the conventional and these efficiencies are greater by 9.61% and 8.26% as compared to conventional BFPP. That means the conventional BFPP has about 11% and 10% exergy and energy and exergy efficiencies, right? And unit-wise exergy analysis also gave some idea about what are the units to be concentrated, right, for the improvement. Right? And this is a final comparison, like ecological analysis shows that the strength of CLC integrated biomass power plant in terms of CO2 emission reductions. Right? So this is about the energy and exergy analysis of CLC integrated biomass power plant. Yeah, participants, if you have any questions in this talk, you can ask now.
Please participate. If you have any doubts, please message in comment box or just talk to you.
So meanwhile, let me open Aspen Plus so that I wanted to show you some simulations, basic simulations, how you can estimate the properties. Just let me. Yeah. So if you have any doubts in that CLC integrated biomass power plant, you can ask.
What is the your lecture was quite interesting and nice to learn, sir, and learn many things. And what is the capacity? What is the biomass used for this experiment, sir?
Sir, why?
Biomass used for this your.
Yeah, this the sugarcane bagasse, sir. So it is sugarcane bagasse biomass.
So, how many cages were used, sir?
I think it is kg per second. I didn't
Okay.
remember the exactly. It is point. It's about close to 1 kg per second or something. Sir, maybe at that figure I can show you in a simulation
Okay, sir.
file.
Nice, sir.
Okay, so
Okay, sir.
just let me open that.
Okay,
Maybe in
okay.
that you
Okay,
can see the exact figure.
okay, sir.
Yeah, yeah. Any other question?
So good morning, sir.
Yes.
So what are the parameters to select the ORC fluids? Is there actually we are
Yeah. You,
but the results should spune and other siloxane fluids are good. But your results shows R600A like that.
Karthi, sorry to interrupt. Your voice is not audible.
Sir,
Some disturbance is coming. I don't
KN
know.
sir, we are getting some disturbances. Can you please check your mic?
Yeah, I think
Uh,
while you
Karthikeyan, can you message in WhatsApp, maybe in message box if you have any doubts? Because your voice is not audible. So,
what I heard, I in my simulation, I said R600 is the R245 Fe is the best suitable fluid. But this study, is meant to see how the performance changing with the different category ORC fluids. I think ORC fluids are broadly classified into three categories: high temperature, low temperature, and medium temperature fluids. Right? Obviously, when you use high temperature fluid, you will get high power output because the exergy quality of energy utilized will be more, right? So as your now low temperature fluid means simply what you have to do, you have to use more thermal oil, right? So that the evaporator will be operated at 200 or 300. Medium temperature means like evaporator can be operated at between 400 to 600, something like that, right? So accordingly, the ORC fluid temperature will also reach 350 or 370, 380, depending upon what's the delta T minimum if you look at. Right, high temperature means the ORC fluid can be evaporated to little high temperatures, right? So if you talk about exergy point of view, obviously this high temperature fluid will give us more ORC turbine power output because the exergy destruction will be less there. Okay, but the thing is, though this gives more power output, I have compared the toxicity of these materials, right? So my decision was based on, though this is giving more ORC turbine power output, I have considered this because this is more eco-friendly than R600A. Okay, but there are different parameters you have to consider while selecting the ORC fluid. Cost, right, and toxicity and operational conditions, right? All these things comes into picture. Katken, I hope I addressed your query.
Yes, sir. Thanks.
Yeah. So just let me show you quickly, since we are talking more about CO2, right? How to estimate the properties of CO2? Like for example, if you want to see pure component properties of CO2, right? You can check directly after entering the CO2 as a component, right? Here you go there to NIST chemistry webbook database, select the CO2, and you can evaluate all pure component properties here. You can see NIST pure property evaluation is in progress. So these are the results. You can see whatever the properties you want related to CO2, right? Pure component properties, you can easily calculate by using this, right? So these are pure component properties, and we also have temperature dependent properties, right? Viscosity, heat of formation, and all those things, but those are not calculated here, right? So if you want to calculate temperature dependent properties, right, so you can do that, by, so this Aspen plus usual procedure I'm not demonstrating because we have not sufficient time to do that. But you can learn from any videos available in net, right? Or Professor Shedbrooks are also recorded few videos in Aspen how to do simulation in Aspen, and that he has one YouTube channel, so you can check that. And there, we have given systematic procedure to do different chemical engineering problems by using this Aspen place. You can learn from that. Okay, so since we are trying to estimate the properties related, depends on temperature, you need a thermodynamic property estimation method to calculate that properties, right? So here, though we can do many things, I wanted to show you this here evaluation of property methods for modeling direct supercritical CO2 power cycles, right? So here the main emphasis on how different property estimation methods calculate properties, CO2 properties, and how accurate they are compared to experimental, right? That is a study done here. And since we are going to discuss about supercritical CO2 power cycle, right? It is used as some refrigerant fluid here. So I think they referred this drift property estimation method, right, is more useful for predicting the CO2 properties at that supercritical stage. So based on this guideline, just let me select the drift property estimation method we have, right? So you can see that pop-up window. So this method used for refrigerants, hydrocarbons, and natural gas systems to estimate the properties. So you select this, right? So once you have selected this, so you can go to again here the pure component estimate, pure analysis, right? So you can select whatever the property you wanted to estimate here, right? I'm going to estimate volume of pure component in terms of meter cube per kilomole, because just I wanted to compare this study. So meter cube per kg at different temperature and pressures they have given, right? So let us see. This data is from, you can see, is from reference book 12, reference 12. It is Paris Chemical Engineering Handbook, right? So let us see now, are we going to get the same property value, right? So now I wanted to estimate the volume, right, specific volume of this fluid, right? Maybe at one data point only I'll take, because we don't have much time. Let me take this. Yeah, maybe this data point. Means pressure pressure 1.785, temperature 250. Okay. So the volume units are different here. Here we have cubic meter per kilomole, right? But anyway, that can be easily converted into cubic meter per kg. Okay. I wanted to estimate the properties of CO2 vapor and liquid, saturated vapor and saturated liquid at pressure 1.785 megapascal. 1.785 megapascal, right? And temperature, I wanted to give range. 250 is there, so let me give 245, 255, increment 5, right? So it will estimate the properties of volume and liquid at 245 1.785, 250 1.785, 255 1.785. So this is the compound we wanted to estimate. Now run analysis. Right. So you can also see this in terms of results. We want 250 1.785, right? So the value is cubic meter per kilomole is this, and but the value given here is meter cube per kg, right? So the molecular weight is 44. So let me divide this with 44, and what we'll get. $255, or what is the temperature we thought of? 250, right? 250, 1.785. Oh, we have same numbers for both vapor and liquid. Something missing. Vapor and liquid, the cubic meter. Did I select the same? cubic meter per kilomole. Volume of vapor and liquid. I don't know why. Yesterday I tried this. We got 230 and 5. Only liquid we are getting. Just I think I'm selecting the different parameter. I may be wrong. Cubic meter per. No. What is this? Megapascal only, right? 1.785 megapascal. Something wrong. Yesterday I tried this. I could get the different properties, but now there is some problem. We are getting both properties same value. Just let me check one value, whether 250, 1.78, 250, 1.785, 2.41. 2.4161 divided by 44. 0.0549. Something wrong in property estimation method or drift prop thermodynamic. Let me this cubic meter per kg run analysis. At 255, what is the value? You can see from results. At 255.05, 1.7.05. Something wrong here. Point for liquid it is 0.009. I think that like this you should be able to estimate. And yesterday I tried with the same property estimation method, reference property method, right? And I could able to match exactly this results given in this table form. I don't know why I'm not getting now. Something I'm missing, maybe. I'm not sure what. And I could see clearly different vapor and liquid profile, which I'm not getting now. I'm not sure what is the problem. Reference property. Same. Pure component analysis, thermodynamic, cubic meter per kg, CO2. Something is wrong. So just you can try this, because yesterday I could see the same properties, right? Pressure and at this given pressure and temperature, right? The fluid, saturated fluid volume and the corresponding enthalpy, right? And the gas and the corresponding enthalpy, I could match exactly the same values. In fact, this table, right? But today I'm not able to reproduce the same thing. I don't know where I'm making that mistake. Let me, no, it takes some more time. I can do this the same thing by using a different form, but only, it takes more time. Like we have to add mixer, then use one stream pure CO2, then you can say pure vapor, pure liquid, and you can do it, right? It takes some time, right? But I wanted to show the other simulations. That's why I'm not continuing this, but you can explore, right? So, and yesterday I could able to see that results properly, right? Exactly, I could able to fit the data, but I don't know why now I'm not getting. Maybe you can try that, and if you have any doubts in it, maybe you can mail me so that just I'll clarify more. I can give more details on this. Maybe after this talk I can try once again, right? And if you really want to see those results, you just mail me the simulation file. I can record it and I can send it to you. And as one participant asked, what is the flow rate you have used in biomass CLC integrated power plant? These things quickly I wanted to show for the remaining 5 minutes. Let me check the property estimation method. Did I consider same? Yes, rift property only. So this is the flow sheet we have simulated, right? As I said, you can do the simulations in Aspen as hierarchical by connecting different units, right, in a hierarchy. For example, this is the sizing, followed by CLC, followed by ORC we have, followed by carbon capture and sequestration pressure, right? So this is the biomass we have considered. Our same thing will be there in this. So mass flows, you can see 0.13, yeah, 0.14 kg per second of wet biomass we have considered, right? So if you look at the operations in each module, we have this wet biomass, right? We are mixing with water, then crushing, so that this moisture inhibits the rise in temperature. So after crusher, we are sending to screen, right? So that we can have a particular size of downstream particles that we are sending into dryer again to remove the moisture content. So that dry biomass we are sending into CLC unit. This dry biomass is sent to first yield unit, because this biomass, as I said, is a non-conventional solid. So we cannot handle as it is that. So that we are converting into elemental form. How much carbon and other things are there, that we are sending into uh, fuel reactor, right, where the combustion happens. Okay, so this is the metal oxide flow and fuel reactor, and the gases are again sending to the next unit, right? So flue gases will be used for energy extraction, right? And this is air reactor, right, where metal oxide will be oxidized, right, again sent back to flue gas. And this is a ORC cycle where we extract power from flue gas, right, and hard depleted air by using this is flue gas, right? And after turbine, this is a hot depleted air, will be transferred energy to thermal fluid. From the thermal fluid, again, the energy will be transferred towards the cycle, right? So where we have this is turbine, right? And recuperators, etc., right? And this is the CCS at the end, whatever the CO2 there in flue gas, right, will be sent to the compressor for increasing the sequestration ready pressure, which is 110 bar. Right, we are increasing the CO2 pressure to 110 bar and keeping ready for sequestration. Right, so this is the whole flow sheet, and we have some power outputs and requirements. Right, so this is the ultimate value we are looking at. Right. So like this, we simulated different power plant configurations, and we evaluated the performances, right, and suggested some efficient process configurations with power production and cogeneration or integration of CCS and CCUs, etc., etc. Okay, so this with this, I would like to end the presentation.